Breaking the wall of the flat world of TV. What three-dimensional television pictures will look like. Thomas Wiegand, Fraunhofer Society, Technische Universität Berlin.
20 years ago, I was at my grandmother's birthday party. We'd already celebrated too much to drive to the border.
Yeah, thank you very much. Happy birthday, Grandma. She's going to be turning 86 this year, and is happy after all. I'm going to be talking about television. So I don't even attempt to create a bridge to the three previous speakers. I'm going to be talking about television. Without television, there wouldn't have been a breaking of the wall, right? If Mr. Schabowski wouldn't have this little thing happening, that he would announce the wall is kind of down. Well, he didn't say it, but he didn't know actually, apparently, the wall wouldn't have come down. And then people thought it's happening, and it was happening in the visual world, and actually it happened in the real world then later. It's pretty interesting that some of you may not be aware that actually in 1989 also the digital media revolution started. At that time, the entire technical development towards digital broadcast and DVD actually took its starting point, and some parts of that were happening in Berlin. About 10 years later, another major step happened in digital media, which was the birth of H.264 in Berlin. And it's the basis of all HDTV. So for instance, every HDTV receiver is going to take this codec, and it's going to be present there. And every Blu-ray player in the future. Most of internet video, as you may know, our young generation is consuming video and entertainment mostly over the internet, and stopped looking at television and Blu-ray discs, and countless mobile video. So within 5 years, about 1 billion devices have emerged from zero within 5 years. What's next? What's going to come after this digital revolution of video? And video is just happening everywhere as we see it. Well, one of the things that we think may happen is high resolution. You are being immersed into the scene. So this is a high resolution cinema that we have built at the Heinrich Hertz Institute here in Berlin. And the lady you see there is the director of the Berlin Philharmonics, and we just have closed a contract with them to also broadcast symphonies. So this is not only giving you a huge cinema display and you're just being immersed into the scene, it's also giving you 3D sound. So you can place every sound source everywhere you like in the room. And there's one thing that goes beyond, and let me show you this movie. I'm going to be interested whether you're going to be seeing this movie.
I saw you two in 3D.
And what did you think?
It was awesome.
The whole movie is going to be defining a whole new genre.
The technology, the 3D, Bono was there, Bono was on, he was on fire. It reached out to you. I mean, you felt his message even more because it felt like he was there and reaching out to you. It was like a spiritual experience.
A spiritual experience? I don't think we are there yet, but this is not the first time I'm hearing that. So 3D cinema is spiritual experience. Is it really happening? Actually is. The number of 3D productions that are coming out is growing tremendously. Obviously, those who produce these movies have some artistical motivation, but they also have a motivation to sell things, and so 3D movies are selling at a higher price. And these glasses that you see from the past are these anaglyph glasses, and today you have polarized and shutter glasses. Why is that? So for 2D, for cinema in 3D, you have two views to be transmitted. And some of the 3D effects you can see already from 2D. So our 2D television kind of works, but not exactly in 3D as you would like it to work. So why glasses? Well, if you want to see an object behind your display and This is your display, and the object you want to visualize behind. The two dots where you look at the display should be spatially apart. The left dot is on the left side, the right dot is on the right side. When the objects are right on the display, the two dots coincide. And when the two dots are in front of the display, the two rays should actually cross each other, and the two dots again spaced apart. So what glasses provide you with, they fulfill you the need to project a different image into each eye, and glasses provide you control by showing different pictures to the left and the right eye. Now, is that sufficient? Some of you wear glasses. Would you want to wear a glass at home? We have asked some opinion about that. So we've asked our chancellor, and no. She didn't like it. So, what to do to please not only our chancellor but everybody else? The solution is an autostereoscopic display. An autostereoscopic display is a normal display, as you can see here, and it has a lens in front of it. So this lens enables us to emit multiple views to different positions so that your eye can see two different views. And you don't need glasses because the display is emitting these two views. Now, if I just emit two views, you just need to stand still and need to mount your head. That's not good working. So I'm going to be emitting multiple views, right? So here in this example, 4, but I need to actually emit more than 4. And the views that are emitted, that's a field of view, and that's repeated. So because I cannot emit an infinite number of views, how many views are necessary? Well, if you calculate it, our perception guys tell us that you should have every 3 centimeters of view. Your eyes are spaced about 6 centimeters apart. So if you say you and your beloved one, you want to watch television together, you probably need 1.50 meters of range in order to have enough of this viewing area. So you need 1.50 meters divided by 3, 50 views. 50 views is a huge problem. It's a huge problem for transmission. So we need 50 times the bitrate for video to transmit to a person wanting to watch video, and we need 50 cameras maybe to acquire it. Actually, the technical solution to this problem is different. What we can do is the following. We can point 2 cameras at an object. This is a brick of the Berlin Wall, 89, and we can point 2 cameras at this object, and then we can try to produce a continuous reproduction of all the intermediate views between these 2 cameras, and then we can do this using a weighted averaging. So how would that work? So let's say you have the left view and the right view, and I wanted to do this because I want to get you excited about engineering. I'm the first engineering talk here. And so you have the left view and the right view, and these are the 2 dots that show the same thing that are in these pictures at the same position. If I want to create an intermediate view, I'm just taking these 2 dots and I'm averaging them. And if, for instance, the view is closer to the left, I'm going to be averaging the left view stronger. That way I'm getting a weight from the left to the right, and I can sweep from left to right in order to show all these views. If I do this, just as I explained, the result is going to look like this. It's not working. What's the problem? Well, let's look a little closer. Let's say you have this object at a distance z from your cameras, and we need to model these 2 cameras. A very simple camera model is the camera plane and the focal points. The focal points have a distance of x. Now, the focal length, which is the distance of the camera plane from those focal points, is f. This object is emitting a ray, and the ray passes through the image plane into the focal points. When it passes through the image plane, it creates an intensity value, which is the actual picture that you are seeing. Now, if I take the ray here and I'm moving it over to the right, this is the copy of this one here, you can see that there is a disparity between these 2 rays. And this disparity is causing the problem that you saw on the first video. The disparity, and this is the first formula of this day, is given as f times x divided by z. F is the focal length of the camera. That's how the camera is built. That's fixed. X is the distance between the two cameras. That's fixed, but I could adjust it. And Z is actually the distance of the object from the cameras. That's the interesting point, the distance of the objects. I need to know how far objects are away in order to reproduce the views between my two cameras. So, and this distance is actually varying. So you can see the disparity becomes smaller when the distance is larger, and it becomes larger when the distance is smaller. You can see from the equation. So what you then need to do consequently is that you need to estimate these depth values. And so things that are closer are getting a brighter value here, and things that are further away getting a darker value. And when you then take these depth values to support your interpolation, because they are calculating the disparity between these two views, you're actually getting a much happier result. This is obviously not 3D. I can't show you 3D on 2D displays. That's not working. And not even this conference is going to break that wall. We still need 3D displays. Outside, when you come in, you see a 3D display. And there you can see our first results on autostereoscopy. So let me summarize. In 3D cinema, 3D is already coming. In 3D cinema, 3D is already coming. At home, we need 3D displays without glasses, for sure. And, well, this is a brave sentence, but let me say it. In 20 years from now, we will look at 2D video like we see black and white video now. I would like to thank a lot of people that worked on this subject, and we had also a lot of support, and we are continuing to work. So the revolution that we are looking at is probably like the revolution when we move from black and white to color. So I have 1 minute left, so let me make a small personal remark. I was born in East Germany, and I was 19 when the wall came down. And when then the money was changed, my parents owned a total of 1 Trabant, some old East German furniture, and 4,000 Deutschmarks. That was it. That was the starting point. And Herr Turner, thanks for doing this, and thanks for having me, and thank you very much.